This is a video on student learning task 4, using transformations of the sine function to model circular motion. Go ahead and pause the video and complete this warm up. You can cross off numbers 3 and 4 in your packet. Okay, at this point, you should have finished this on your own. So let's take a look. Number 1, we're given sine of 75 and we're asked for 3 equivalent statements. First off, we want to remember that sine of theta can be written as y over r. We want to realize that 75 degrees is in the first quadrant. So I'm going to draw 75 degrees in the first quadrant, 75. Now I know 75 has a y and an r, so I'm wondering what also will have the same y and r value. So if I put that reference angle of 75 degrees in the second quadrant, I find here I have an angle of 105 degrees. So that they will have the same sine value because they have the same y and r value. Now here, when I look at the next statement, there's a negative in front of it. So I'm looking for what has the opposite y over r. So if I put 75 degrees in the fourth quadrant, it will have a negative y value because that goes down. Right, like if I go x, y, it goes left and down. So the x and y are both negative. R is always positive because it doesn't come from the ordered pair, it comes from the Pythagorean theorem. So here, if I have this negative here and I go negative and then negative y over r, I'll get the same y over r as I would from sine 75. So then in the third quadrant, I'm going to do 180 plus 75 and I get 225. Sorry, 255. And then if I do the same thing and I put it in the fourth quadrant and I have negative y over r, again, the negative in front of the sine will cancel off the negative in front of the y and give us the same y over r as 75 degrees. And that's going to be 285 degrees. And of course, you could switch these last two. That would be okay. So then we're going to apply a similar approach for 30 degrees. If I put 30 degrees here, it has a y and an r. And if I put it in the second quadrant, I'll have the same y, r. So 180 minus 30 means in the second quadrant, I have 150 degrees because 30 and then same thing here. If I have a negative in front, I'm looking to have negative y over r to get the same y over r. So 30 degrees here, 180 plus 30 gives me 210. And then over here, 30 degrees, 360 minus 30 gives me 330 degrees. And again, these last two you can switch. So number 5 and 6 are telling you that this ordered pair is a given point on the circle. I'm not going to draw the circle because my circles are bad. We're just going to, imagine there's a circle here. So we have 1, 2, 3, 4, 5. We have this point. And I'm going to label my triangle really nicely. Here I have a length of 1. Here I have a height of 5. And here I'm going to go 1 squared plus 5 squared equals r squared. 1 plus 25 is 26. If I have 26 equals r squared, that means the radius will be the square root of 26. So now the sine value is going to be y over r, cosine x over r, tangent y over x, and I just can't leave it like that. I'm going to make it 5. We're going to do the same thing for number 6. And get my straight line tool going on here. I've got negative 2, 3. So negative 1, negative 2, 1, 2, 3. Here's my triangle. So again, negative 2 squared is 4, 3 squared is 9. I add those together. I get a radius of my circle of the square root of 13. Sine y over r, x over r, and y over x. You could also write that as -3/2. Okay. So just a couple announcements. There is homework and a quiz this weekend. Please make sure that gets completed. All right. Here are the answers to last night's homework. They were posted in our class notes. Feel free to pause the video if you need to review those answers. So today we are going to look at the sine functions and how changing the Ferris wheel's properties will change the graph of the function. So as a reminder, going back to Carlos and his Ferris wheel, we're going to stick with, we made assumptions for Carlos's Ferris wheel. We knew that he had a radius of 25, the wheel was 30 feet above the ground, one complete rotation every 20 seconds. If you go back to the page where we wrote that equation, we're going to use the format of that equation again today. Now, number one asks us to create our own description. Just so we have the same graph, we're all going to use a Ferris wheel that has a center that is 40 feet above the ground. So go ahead and mark, this is 40. We're all going to have a radius of 10 feet. So go ahead and mark this 10. All right, and we are all going to make one rotation every 16 seconds counterclockwise. And we're going to do this so that it fits nicely on the graph and you'll be happy, trust me. So the first thing I want to do is I want to create a table. All right, so I've got this graph here. We're going to make a table. Time, height. Okay, so we've got time is 0. We know when time is 0, we are at 40 feet above the ground. Now I'm going to go all the way around. I'm going to kind of think about my key points here. I'm going around. I know this goes all the way around in 16 seconds. So if I divide 16 by 4, 0 seconds, this is going to be 4 seconds. This is going to be 8 seconds. This is going to be 12 seconds. This is going to be back at 16 seconds. And I'm going to think about the heights at these times. So go ahead and fill in your table height at 4, 8, 12, and 16 seconds. So you should have filled in that the height of 4 seconds is going to be 50 feet because 40 plus 10. The height at 8 seconds, we are back at 40 feet. The height at 12 seconds will be 30 feet because we're going to subtract the radius from the height above the ground. And then at 16 seconds, we are back at the starting point. So let's go ahead and graph these points. Like I said, like the 16 seconds works out good. We have 0, 40. We have 4, 50. 8, 40. 12, 30. And you can see if we were to continue a second rotation of our Ferris wheel, it would come to the top and then to the middle and then to the lowest point on the Ferris wheel, all in, for as long as they're going to let you ride the Ferris wheel. And maybe the ride operator is really nice and you get to ride a lot. So if you only get to go around twice, that's not fair. Now we're going to try to make as smooth as a curve. We don't want it to look like a zigzag. Don't make it look, oh, that was not so good. We really want it to be a nice smooth curve. We don't want to do this. This is a very nauseating ride. Don't do that. All right, so we want it to be a smooth curve. And we want our curve to have arrows at the end. Now, it really doesn't make sense to put arrows at the beginning because we're not going back in time, but we're going to put an arrow here. If this was a graph, not in a word problem, we would put an arrow on the left side also. So number 3 is asking us for the equation of this graph. So I really encourage you to turn back where we wrote the equation for Carlos. We had y equals, or h of t equals Then there was something here, then it was sine, and then there were some parentheses and a T or an X, and then plus something. Go ahead, pause the video and see if you can fill in these 3 spots. Okay, hopefully you put in the very front, you put 10 because that's always the radius of the wheel. And over here at the end, you put plus 40 because that's always the height above the ground of the center. And then right here, we need the degrees per second counterclockwise. So let's think for a second. We are moving 360 degrees counterclockwise in 16 seconds. So if we divide that and like, I just want to model for you, like you don't need a calculator for this, guys. These are even numbers. Like I can be like, hey, I'm going to reduce this. I have 180 over 8 and I can reduce that again. And I have 90 over 4 and then I can reduce that again. And I have 45 over 2. So you can put 45 over 2 here, but like I can divide 45 by 2. I'm not scared of that. I know it's going to be 22.5 degrees per second. That's an ugly 5. I can do better. Okay. So this Ferris wheel is moving at 22.5 degrees per second. So what I would like you to do, I'm going to go ahead, pause the video. I want you to, there's a link at the top. If you would like to follow along with me, go ahead, write that link down and open it in a separate window. Right, number 4 is asking us, how would the graph change? The graph, how would the graph change if the radius changes, if the height changes, if the wheel rotates faster or slower? So I want to think about the location of the radius. The radius is the coefficient of sine. So if you open that link, you see this really nice Ferris wheel. Okay. So I'm going to make the adjustments. If you want to follow along with me, apparently I need to hit reset, which is a little odd. Or not. Uh-oh. So here, if I change A, you can see the wheel itself gets really, really big. What happens to the graph as I make the wheel, oh, there it goes. If I make the wheel bigger, what happens to the graph? Well, what happens to the graph is we have, as you saw, a vertical dilation. Now, what if I change the center of the wheel? So let me go back to our picture. I'm going to make that a little smaller because it's like kind of hard to see. Take it back to 1. Okay, so now I'm going to move the D. And if I move the D, if I move the wheel, you can see the wheel's moving up. Whoop, and it's gone. Bye, wheel. And I'm going to bring it back down. What happens to the graph as I move the Ferris wheel up and down? What's happening to the graph as the Ferris wheel moves up and down using good math vocabulary? We have a horizontal translation. Okay. Sorry, not a horizontal translation. I don't know what that was all about. A vertical translation. Woo. Okay. All right, now what if the wheel rotates faster or slower? I kind of love this one a lot. This one might be my favorite. So let me go back to my Ferris wheel and I'm going to bring, I actually kind of like it like, let's bring it like at 1. So if I'm rotating my wheel faster or slower, you're not touching this C here. You're going to touch this B one. Don't touch C. All right, so if I rotate the wheel faster, and I'm actually going to animate this because it's kind of fun. So you can see it's going fast. Now it's going slow. I can make it go real slow. Oh man, this is the boringest and it's dead. So there's a really slow moving Ferris wheel and you can actually see it's moving slowly. I'm going to pull this out a little bit so we can get a nice view of this graph because it's a nice graph. All right, so There's a slow, and I'm going to speed the wheel up. So if you get motion sickness, don't ride this one. Oops, wrong thing. There it goes. Oh my gosh, look how fast it's going. And now it's going to go faster and faster, faster. And now it's going to be a very intense Ferris wheel. Oh my gosh, people are going to get thrown out. There's going to be deaths. It's going to be on the news. Crazy stuff. What happens as the Ferris wheel goes faster? This is a really exciting point because this is the first time we really can see this transformation. We have a horizontal dilation. As the Ferris wheel gets dangerously faster, we can see horizontally the graph is being compressed. But as the Ferris wheel gets slower, we can see that the horizontal dilation stretches out. The horizontal dilation gets wider. So again, faster Ferris wheel, more compact graph. All right, so there is a horizontal dilation as the wheel, rotates faster, the graph is more compressed horizontally as the wheel rotates. I cannot spell. There it is. Or maybe you can't type, or maybe both. Slower, the graph is stretched out. Like you can almost imagine like people are like holding the ends of the graph when it gets slower and it's like literally stretching it out like a spring. Like if you've ever taken apart a ballpoint pen and there's that little spring and you pulled on it and you stretched it out, it's like the same thing. Okay, so now we're talking about the equation. So what changes in the equation? We're going to be really specific. Where do I change the equation if the radius of the wheel changes? So we want to be really specific, and that is the coefficient of sine is going to change. Okay. The radius of the wheel is shown in front of the sine. It's the coefficient of sine. The height of the center of the wheel, that's going to be our constant that we are adding or subtracting. If the wheel rotates faster or slower, I'm going to say the coefficient of the independent variable because some of us like t and some of us like x, and I'm not going to judge. Okay. So number 6 is going to ask you to write some equations, and I'm actually going to ask that you pause the video and work on those. But before you do that, I just need you to notice 2 things. First off, I need you to notice that you are straight up given the speed in 6A. And then in 6B, I want you to notice that we are now rotating clockwise every 15 seconds. So go ahead and pause the video and try to write these 2 equations. All right, hopefully you worked on these on your own. So for letter A, we have height at time t. So the radius is 30. So we're going to start 30 sine. We are directly given the degrees per second. So we're going to have 15t. And the center of the wheel is 45 feet above the ground. So there we go. Letter B is a little more challenging. We know the radius is 50. We know that the center of the wheel is at ground level. Okay, so I'll know half the time is spent underground, so I don't need to add anything. But I'm moving clockwise, so I'm going this way every 15 seconds. So I want to make a little note here that every 15 seconds, I am moving negative 360 degrees because we measure negative angles clockwise. So if I divide that by 15 seconds, and I divide that out, I'm going to divide these both by 3, and that's going to be negative 120 over 5. And 12 goes in once, twice. And then there's the 20 left over. So it's going to be negative 24 degrees per second. So here I'm going to have negative 24 T. Again, this is because we are moving negative 24 degrees per second. The homework for tonight looks like this. It's in your packet. It's also posted on my MCPS. I want you to take the time to define the following terms. It makes a nice study sheet. When you have to go back, go look everything up, provide some examples, maybe that would be a good idea. You can cross off nah, we'll leave them. Try them out. Try them out. So this is tonight's homework. Answers are on Drive. There is a quiz this weekend. Have a great weekend.